I almost completely forgot to talk about one of the most important carbon-carbon bond forming reactions, especially with regards to aromatic chemistry. It is an electrophilic aromatic substitution, and there's a couple of dead guys that came up with it, named Friedel and Crafts in Germany and England. So this is a really important notecard reaction that we're actually going to develop over the course of an entire lecture video here. So, as I said, one of the most important things to know about it is a CC bond former, and we know whenever that is true, it gives us special prominence because it'll lead to all kinds of interesting synthetic capabilities. And so let's just kind of see an example of it, and I'll just start off with plain old benzene here. And the clarion call that Friedel Crafts alkylation is about to happen in your brain hole is the presence of an aluminum chloride catalyst. Turns out that this is really, it's not the only catalyst, but it's the one that you most commonly see, especially on ACS exams and various homework problems and things like that. And whatever that aluminum halide happens to be, by the way, it doesn't have to be chloride, but if the other reagent that you use involves a chloride, you got to make sure to include an aluminum chloride. If it was a bromide, you'd do an aluminum bromide, etc., etc. And what we're going to do is we're going to just take some sort of species like this. We'll make it an ethyl chloride. And it turns out that if I do these conditions, we will end up with sticking a new carbon-carbon bond right onto our aromatic ring. And it happens in high yield, and it's really easy to work these kinds of reactions up. Hopefully you can actually see that. So of course we got to go through the mechanism. The mechanism itself is pretty simple. Just keep in mind the importance of showing some sort of pot sweetening step in most electrophilic aromatic substitutions. So that's actually the first thing that we're going to do. And it does have a lot of analogy to the halogenation reaction in the sense that this Lewis acid catalyst is essentially going to weaken the bond that we see between this chlorine and a carbon right there. And I think your book itself actually shows this mechanistic protocol a little bit differently, but it's never a wrong thing to show some sort of pot sweetening step. In your book, I believe it actually might show this chlorine just like popping off completely. The problem is that this reaction, if it forms that primary carbocation, I don't necessarily like to show it. Really, this species is almost, you can almost think of this as in kind of an equilibrium with the aluminum tetrachloride, and this thing very closely associated with it as a positive charged cation. But either way, showing it like this is not going to be that big of a deal. And so at this point, we're going to swing this bond out just like we've seen a couple of times before. And we are going to successfully put this, oops, my arrows are getting a little messy here. I guess it's more this arrow. And of course, you get to one of those really typical looking tetrahedral intermediate electrophilic aromatic substitution kind of intermediates here. And of course, if I wasn't incredibly lazy, we would go through and we would show all the possible resonance forms here. Obviously, if there was any kind of substituent with a lone pair of electrons out here, that would probably necessitate the use of a fourth type of resonance form out here. But we already have seen how to do that, so I'll kind of leave that up to you. Final step of the mechanism, keep in mind, is almost always going to be reforming your catalyst. That's why it's allowed to be in a catalytic amount. And so we've got our aluminum species here, and we are going to have this bond swing out, attack the H, and reestablish aromaticity. And we end up with our product. So that's Friedel-Crafts alkylation. It turns out that it's as I said, it's a really easy reaction to do. The problem is if you happen to have some sort of reagent that could possibly rearrange due to some sort of carbocation rearrangement, it's sometimes tough to get the product that you want. So I'll show kind of the prototypical example of where, in a synthesis you might say want a certain product, and I'll show you the problem with it, and then I'll show a solution. Okay, so let's say that this was a synthetic target. And we decided that we had some benzene and we wanted to do a Friedel-Crafts alkylation, right? Kind of thinking backwards here, you'd say, well, I could probably, create that bond through a Friedel-Crafts alkylation. And in a perfect world, this kind of thing should work, right? Right? But it turns out that if you were to use this reaction, what happens is that there's enough of that kind of carbocation that could possibly rearrange. So in this, we'll just kind of abbreviate like a mechanism and think, well, what would this catalyst ultimately lead to? It would really lead to the equivalent of this, right? And because this thing can very easily rearrange to a slightly better substrate, it most likely would. And so the product that we would actually isolate from a reaction like this would actually be consistent with the carbocation actually looking like this, such that instead of getting this product, you would end up very likely getting a rearranged product that looks like that. And of course, like that's not what we want, right? So there has to be some sort of way to kind of work around this because it's such an efficient reaction. And it turns out that these same two dead individuals came up with what's called the acylation that is going to require one additional step, but the advantage of it is that it avoids any kind of rearrangement. Okay, so notice that I kind of redrew our goal product over here. And we're going to be talking about the Friedel-Crafts acylation as opposed to the alkylation. An acyl group is kind of an old-timey way of talking about essentially ketone groups. Acyl, that's something where you kind of automatically think that you have some sort of moiety that kind of looks like this. Right? And so we'll talk about a whole bunch of different acylations. In this particular case, what we're going to be using as our acylation substrate is this, right? And so this product, this starting material is ultimately going to allow us to get to something that looks like this. And even though the Friedel-Crafts acylation can kind of be a standalone thing, which you'll see in just a second here, it's most often employed in a case where you want to alkylate something and you were worried about rearrangement. They're also, due to the fact that we're going to first introduce a ketone type of group, it's also going to kind of do that meta-directing, right? And so it's commonly the case that you'll introduce that ketone group onto the ring, you'll use it as some sort of meta-director, then you'll do a second step that gets you to just the alkyl chain, and then of course it's an ortho-para-director, and so it's kind of going to be a synthetic protocol that we'll see eventually, most likely next week, by the way. So let's say that's my target, right? And I have to start with benzene. The way that I'm going to do this is instead of starting with the alkylation material that I really would like to start with, I am going to start with this compound right here. And to be totally honest with you, the mechanism is very good, also in your textbook. I'm not going to go through it because it's really similar to what we just saw before. The only difference is that you end up with what's called the acylium cation. In other words, a carbon with a positive charge there due to the chlorine kind of falling off onto the catalyst. But the good news is that we're going to be able to attach that group But you'll notice that we're not quite there, right? This step right here is going to involve some sort of reductive step, right? Anytime that you kind of remove equivalents of oxygen, it turns out that we're actually reducing an organic compound. Eventually, we'll actually go through and kind of calculate oxidation states for all kinds of different things and learn all the kind of ins and outs of oxidations and reductions. But that's going to kind of wait until we get to carbonyl chemistry. For now, just take my word for it that removing an oxygen and replacing it with H2 is in fact a reduction. It turns out that this step can be done in a whole variety of ways. So let's just label it with A here, and I'll give you the reagents that we could use to remove that thing. Well, one really common reagent is to use basic conditions. This is also termed the Wolff-Kishner reduction, which I may misspell. Kishner. It may be Kishner or Kishner. Anyway, Wolff-Kishner reduction. And so the reagents for A in that case, you would choose this based on, let's say, if you had in your aromatic ring some sort of group that was really sensitive to acidic conditions, you might go with these basic conditions for the Wolff-Kishner. And typically the reagents are going to involve rocket fuel, aka hydrazine, a whole bunch of base, and a whole bunch of heat, right? Those are pretty extreme conditions, but the good news if you do that kind of thing, it is really good at removing those benzylic, this position is called the benzylic position, so benzylic carbonyl groups. The other is, of course, if you have some sort of group that's maybe sensitive to basic conditions on this ring, in that case you'd use acidic conditions. And probably the most common thing that you would see is what's called the Clemenson. And again, I'm not sure I'm spelling that right. The Clemenson reduction. And probably the most common way of doing a Clemenson was probably with HCl, and I think it's a zinc-copper couple, but I better check that. Oops, I've made the first mistake that I've ever made. This is not a zinc-copper couple. This is a zinc-mercury couple. So, again, this is, especially the Clemenson reduction and a little bit the Wolff-Kishner. It's also going to be something that we see in non-aromatic chemistry. It turns out that especially this one is a really good way of just completely reducing away carbonyl groups in certain situations. But this is really the first time that we're going to see these guys. So you can see kind of the synthetic utility of this. And as I was referring to before, if for some reason you wanted to introduce this group to take advantage of its meta-directing ability, you could, instead of doing this right away, these reductive steps, you could actually introduce some sort of substituent in the meta position and then do one of these steps, and then suddenly that thing is going to be an activator for ortho and para. And so that's a really common thing that you'll see in some synthetic protocols. So that's going to end our discussion of Friedel-Crafts alkylation and acylation. You've got a couple of homework problems having to do with this. But one thing I did want to show you is another named reaction that kind of gets out of a little bit of a problem with doing Friedel-Crafts when it's a really, really simple, just one carbon homologation that you want to do. So one thing you'll start to pick up on about a lot of these named reactions is that they're really just kind of like small variety, like really slight changes on other named reactions that you've already seen. I always made me giggle because, it's kind of like somebody just like changed maybe a solvent or like put a methyl group where there used to be an ethyl group, and then they get to name it, according to themselves. So I got to come up with a really good Breslin reaction one day. And so the Gatterman-Koch is a good example of something that's really a Friedel-Crafts acylation, but kind of has a little bit of a twist, right? So let's say that our synthetic target was this pretty simple benzaldehyde species. Right, so here's benzaldehyde. Well, it turns out that if you were thinking of maybe, having the equivalent of this, and just use that as a starting material with your aluminum chloride catalyst, it turns out that there's a lot of problems with having this thing existing in real life. So what essentially the Gattermann Coke does is it kind of it synthesizes that kind of in the reaction conditions. So a really good note card reaction that's like super specific to just this group. And we'll find out that aldehydes are actually pretty important synthetically, which is the reason why so many named reactions involve them in some way. Really what you're going to do is you're just going to treat this thing with carbon monoxide and HCl. And it turns out, and I think the mechanism is in your book, but essentially you're going to be doing the equivalent of forming this in the kind of this pot sweetening step, and then we're going to be able to pop on an aldehyde. Really good note card reaction. I should mention before we stop talking about Friedel-Crafts acylations and alkylations, there are other kind of Friedel-Crafts acylation looking reactions where, or I should say alkylation, where let's say I have I don't know, an alcohol or something, right? So let's say I have that kind of alcohol and I have some catalytic acid of some sort. Right? Well, it turns out that there are reactions that are electrophilic aromatic substitutions, and let's just say some random catalyst here, that really what you're doing is you're forming that carbocation essentially, right, through kind of the beginnings of an E1 mechanism right there, right? And so even though technically it has to have aluminum chloride and your either acyl chloride or alkyl chloride type starting material, really if you're doing this to a benzene ring, right, in order to get to this thing, it may not technically be a Friedel-Crafts alkylation, but you're really doing the exact same thing. So kind of keep that in mind. When we get, especially into third term, what we're going to start doing is we're going to learn to kind of generalize types of reagents, because it's just the fact that a lot of times we're not going to specifically talk about a reaction, but if you kind of have a general idea of how things react, you have a really good chance of kind of reasoning by analogy to something else, right? So if I were to see something like this, I might kind of get confused for a second and think, what the heck is this going to be doing? And I might say, well, these conditions very likely is going to lead to some sort of carbocation, and maybe they want me to do an electrophilic aromatic substitution. So just kind of a real, quick, thing to mention. With that said, let's get on with it.